Hello and welcome to this video. In this video we're going to be going through the photoelectric effect. So we've said before that the photoelectric effect is the evidence. So this is the evidence for the particle nature of light. Okay, so evidence for particle nature of light. Okay, and we said the particle nature of light is that it's a photon. Okay, so we're going to be looking at how can we prove that light is a photon using experimental evidence, because that's how we have to prove everything. And so what the photoelectric effect is, so the photoelectric effect is the effect that if you shine, if light of a high enough frequency, so you have to get enough energy to be able for this effect to happen. If light of a high enough frequency is shone onto a metal surface, the surface will release electrons. Okay, so this is quite a weird thing. So just firing light energy, it's usually ultraviolet energy, onto a metal surface can cause electrons to be emitted from the surface of that metal. How does that happen? Well, let's imagine we have some metal surface here, and we've got atoms in them. I'm just going to draw the electrons because it makes it a little bit simpler. But if you imagine each of these electrons is on the outer edge of an atom, or even since this would be metallic bonding, you'd get some of them that would be just in the sea of delocalized electrons just flowing around. But if we have electrons near the surface and we have a photon coming in, this electron might absorb that photon and then gets emitted as what we call, I'm just going to do it like this. This is what we call a photoelectron. Okay, because it's an electron that's absorbed the photon, so it has more energy. And if the energy of this photon is sufficient enough, so if we have high enough frequency, meaning high enough energy, then when this absorbs, it has enough energy to escape the surface of the atom. And this is the general idea of the photoelectric effect. Okay, and this seems pretty simple, but when we actually change a few things and look at a few more in-depth details of the photoelectric effect, it becomes clearer that this is kind of a very weird phenomenon to happen. Because let's assume, so let's assume we're going to use the wave model to predict what's going to happen to this. Okay, the wave model predicts that the light source is providing continuous energy. Okay, so continuous energy from the wave means that after some time, if the electron just keeps absorbing loads of energy, then after some time it will always have enough energy to be emitted from the surface. It's just going to have some time delay. So continuous energy from wave means after some time the electron will be emitted. Okay, and so what we can do is we can look at the power output of the light source. So it's usually either a UV bulb, can sometimes be a laser if we need it to be, but we can see the power output of that light bulb. We can calculate that pretty easily. And so if we know the power output of the light bulb, it means we know the rate of energy transfer per second to the electrons. Okay, And if we know that, we can then calculate, if we know the rate of energy transfer, we can calculate how long should it take for this to be emitted. And it's usually on the order of a few hours, okay, which is a very long time to wait in a lab. You'd just be sitting around for hours waiting for the light to finally release electrons. But it's not so long that we'd never be able to see it, right? So we can actually carry out this experiment, leave it for a few hours, and then see what happens. And in practice, this time delay is never observed, okay? So time delay is not observed. Okay, and this is our first piece of evidence that the energy can't be continuous from this light source. Okay, so this means the time delay is not observed, so there must be discrete energy. Okay, and then it would be completely natural to assume that why can't a single electron absorb 2 photons and then have enough energy? Because surely if it can only absorb 1 photon at a time, it could have just absorbed 2. And so the way we can investigate that is by increasing the intensity of the light source. So in the wave model, if we increase the intensity, what we're doing is we're transferring more energy per second, and that means that we will have more energy there, or it will take less time. That we know isn't going to help, because we know no matter what the rate of energy transfer is, we don't see any time delay anyway. So instead of that, we're thinking, surely if we're transferring more energy and we're not increasing the amount of energy that a single wave would have in terms of photons, we're increasing the amount of photons that we have, but they all have the same energy. Okay, so let's just scroll up a bit so I have a little bit of space. So if the intensity of light is increased, what this means is that we emit more photons. Okay, so we're not actually increasing the energy of each photon, but we've got more photons, each with the same energy. So we have more packets of energy that are being transferred. And so if we're emitting more photons, that should have the effect that more electrons could be emitted. And then we can calculate the amount of photons that we're emitting, since we know the intensity, and we'll know the frequency because we can set that to be whatever we want. We can calculate the number of photons, and what we find is that if this energy is sufficient, the number of photons will be equal to the number of electrons. So what we see is there is a 1-to-1 ratio of photons to electrons, which means only one photon, so only one photon can be absorbed by an electron. And if that energy is not enough, then it's not emitted. If the energy is enough, it will be emitted. Okay, so this is our second evidence that this has to be a particle model, because if we can only get one photon per individual electron, it means that we definitely don't have a continuous energy source, because we have very discrete packets and it can only be one discrete packet per electron rather than being a continuous wave source. So you can think of the wave model as kind of like fueling up cars. So it's fueling up the electron. As soon as the electron gets enough energy, it goes off. That same wave can then just be transferred to another electron, fuel that up, and that goes off. But we don't see that happening. What we see is each electron needs its own fuel source, essentially. It needs its own photon to be able to charge it up so that it gets enough energy so that it can be released. Okay, so now we have the basic idea of the photoelectric effect, and we know now why we believe that or why we know that the photon has to be a discrete energy source and why it has to behave as a particle. Okay, now as everything with physics, we have to add in a bit of maths, and so we're going to look at the photoelectric equation. Okay, so the photoelectric equation is quite a simple equation actually. It looks scary because it's got loads of Greek symbols, but it's actually nothing too complicated. So what the photoelectric equation says is essentially energy is conserved, right? So if we've got a number of an amount of energy given by a photon coming in, that energy has to be used to release the electrons from the surface, and then any excess energy that they still have will go to kinetic energy. If they don't have any kinetic energy excess, then they'll just stay stationary. So what we're saying is the total energy input has to be equal to the total energy output, which makes sense. That's just conservation of energy. Our total input is HF, okay, because this is the energy of a single photon. So that single photon needs to then be used up with the energy sufficient to release an energy from the surface of this metal. That energy we call the work function. Okay, so this is the work function. We're going to talk a little bit more about this in a second. And I said any excess energy, so if this is our total input, our total output is going to be the work function plus some kinetic energy. This is a maximum value, okay? This is very important. There's very common questions asking why is the kinetic energy a maximum value, and we'll talk about this now. So this is your photoelectric equation. The work function is what we'll start by looking at, and the work function is, as by definition, the minimum energy required to remove an electron from the surface of the metal. Okay, so the minimum energy required to remove an electron from the surface of the metal. The key word here is it's the minimum energy, okay? And this work function, so this is by definition, some things that we have to note is this is obviously an energy, so we measure it in joules. Sometimes, or most of the time, they'll give you it in electron volts. So you have to convert into joules, which 1.6 times 10 to the minus 19 joules is 1 electron volt, so you'd be able to do that. The work function is specific to each metal, so every metal will have its own value for the work function. So it's more like a property of the material itself, specific to each material, okay, or each metal. Okay, then another very common thing they're going to ask you is why is this a minimum value? Okay, so why this is a minimum and why the kinetic energy is a maximum are kind of two parts or two sides of the same coin, okay? Because the way you can think about it in terms of just the maths of this is if we know HF is a constant value and this is a minimum, then surely as this starts to increase, as the work function begins to increase, the kinetic energy has to decrease to keep it to the same value, okay? But why does the work function increase? If it's specific to each material, surely if the material is the same, then the amount of energy required to release the electrons is the same. But we have to look on more of a three-dimensional scale. So if we imagine we have the surface of the metal, so I'm going to draw this in 3D as best I can. This is the surface of the metal, and we have loads of photons that are all incident on the surface of the metal. So electrons at the surface of the metal will be released with the least effort possible, but this is a three-dimensional material. So electrons down here, deeper in the surface, are going to need more energy to actually be released from the surface, okay? Probably shouldn't put a bottom on this because this could keep going even further as well. But the point still stands. So the lower an electron is inside the material, the more energy it needs to escape the material, okay? And so y is the work function a minimum. That is just because in order to, so electrons deeper in the surface require more energy to leave the surface. Okay. So electrons that are deeper in the surface are going to require more energy to leave the surface, and therefore this has to be the minimum value, because this is just the energy to release the surface electrons. So the electrons are right at the very top of the surface. Okay, so this is the work function. Then we go on to the y is kinetic energy a maximum. It's going to have a very similar answer. So let's just make some room for this. So y is kinetic energy a maximum, and the reason is because the kinetic energy that's put in is the excess energy from any of the leftover energy. So it all gets used up in the work function first, then any excess energy that we have transfers to kinetic energy as soon as they've been released from the surface. So it's a maximum since electrons deeper in the surface require more energy to leave the surface. To leave the surface. So they have less excess energy. Less excess energy to be converted to kinetic energy. Okay, converted to kinetic energy. So this is these are some very common questions for them to ask on the photoelectric effect. The work function, what's the definition, what's meant by the work function, why is it a minimum, and then why is kinetic energy a maximum.